Welcome to this new Inside Code video where we'll see the count good nodes problem. So what does the problem say? It says, given a binary tree root, create a function that returns the number of good nodes. Node n is called good if there are no nodes that are greater than n in the path from root to n. Here is an example. We have this binary tree and you can see that we have 7 good nodes. An example of a good node is this one. We consider it as good because all the nodes in the path are not greater than 5. And this one is a bad node because in the path we have a node that is greater than 3. The intuitive way to solve this problem is that for each node in the tree we traverse the path from the root to that node, and if we didn't find any node that is greater than n, it means that we found a good node, so we add 1 to our output. This solution works, but it's quite slow because we always need to retraverse nodes uselessly. We end up with a time complexity of O of n times h, where n is the number of nodes in the tree and h is the height. In order to optimize this solution, we will use a variable maxNode that will hold the maximum value that we found in the path from the root to the actual node so far. Then by comparing maxNode with the value of the actual node, we can know if it's a good one or not. An example is better to understand. Let's do this one. The first call goes on the root, and you can see in the call stack that the second parameter is the maxNode we've seen until now, and we didn't see any node yet, so the initial value of maxNode is minus infinity. In this node, 2 is greater than minus infinity, so it's a good node. Now we count the number of good nodes from the left. Here you can see that the max changed. It became 2 because 2 is greater than minus infinity. It replaced it. This node has the value 1, and max node is 2. 1 is smaller than 2, so it's a bad node. We continue from the left, the max remains 2. 2 is not greater than 3, so this one is a good node. From the left, we have null is the base case, so we directly return 0. From the right, same thing, we return 0. Now we got the number of good nodes from both sides and the actual node is good, so we return 1 plus 0 plus 0, which is 1. Now we go to the right, 2 is not greater than 5, so this one is a good node. From the left, the max became 5 but is not greater than 6, so we have a good node. Left side, null. Right side, null. And the node is good, so we return 1 plus 0 plus 0. Now from the right, null, we return 0. We have 1 from the left, 0 from the right, the node is good, so we return 1 plus 1 plus 0, 2. Now we have 1 from the left, 2 from the right, and the node is bad, so we return 0 plus 1 plus 2, which is 3. You can see that we counted the number of good nodes from the left, we found 3, and now I'll just let the animation count from the right side. We finished the recursive process and we got 1 plus 3 plus 3, which is 7. The tree contains 7 good nodes. Now we can move to the code, but before, please take some seconds to like the video and to subscribe to the channel. In code, our function takes as parameters a node from the tree and the variable maxNode that starts at minus infinity. The base case is when the node is null, we directly return 0, we have no nodes at all. Else, we first check if the actual node is good. We can know it by checking if maxNode is not greater than its value. Then, we get the number of good nodes from the left and from the right. But look at the second parameter, we are passing the max between maxNode and the value of the actual node. Now that we got it from both sides, we return isGood plus left plus right. I know that isGood is a boolean, but in this expression, it will be equal to 1 if it's true and 0 if it's false. We did that because we want to add 1 when the actual node is good and 0 when it's not. You can see that this type of solution follows what I told in how to solve almost every binary tree problem video. I told you that in the recursive case, we call the function on the left subtree, we call the function on the right subtree, and we join the results. And it's exactly what we did here. For the time complexity, here we are just traversing the tree once, so the time complexity is O of n, where n is the number of nodes. And for the space complexity, the maximum call stack size is reached when we are at the bottom of the tree, and we are not using extra space in the call, so the space complexity is O of h, where h is the height of the tree. I hope that you enjoyed this video. Please comment below what you thought about it, and see you in the next one.